Hi everyone, and welcome to our talk, Raging against the Machine Clear, a systematic analysis of machine clear and their implications for transient execution attacks. My name is Hany, and this is a joint work with Enrico Barberis, Herbert and Cristiano Giuffrida from the Vrije group in Amsterdam. During this presentation, you will also be hearing from my co-author, Enrico. Modern processors use speculative execution to optimize performance, and one of the most common speculation techniques is branch prediction. Consider the snippet of code where we access the array only if the index x is within the array size. Let's assume that for some reason, for example, memory latency, the size of the array is not known yet. Therefore, the condition cannot be evaluated. The CPU will transiently execute the array access at the index x, speculating that it is inbound. Later, when the array size is known, the CPU will see that x is not within the size and will revert the speculatively executed instruction. But even if instructions are reverted, they still can leave an observable microarchitectural trace, in this case, a cached line. Intel defined bad speculation as the root cause of discarding issued instructions on x86 processors. And there are two main types of bad speculation. The first one is branch misprediction, where the branch predictor mispredicts either the direction or the target of a branch, as we saw earlier, causing a squash of all instructions executed within the mispredicted branch. The second type of bad speculation is called machine clear, where a machine clear condition flushes the entire processor pipeline and restarts the execution from the last retired instruction. While all previous transient execution attacks are built on top variants of branch mispredictions and Intel TSX, which is now not supported anymore, to create transient execution paths, the class of machine clear remains widely unexplored. In this work, we performed the reverse engineering and the security analysis of the main root causes of the class of machine clear, which are self-confined code, floating point, memory ordering, and memory disambiguation. In this presentation, we will only present self-confined code and floating point. You can read our paper to know about the other two types. We'll present two novel machine clear-based transient execution attack primitives. The first one is called Speculative Code Store Bypass, which is based on a self-confined code machine clear. And the second one is called floating point value injection, which is based on a floating point machine clear. We will also present an end-to-end floating point value injection exploit, which transiently leaves arbitrary memory in Firefox web browser with a leakage rate which can reach up to 13 kilobytes per second. To analyze the different types of machine clear, we try to understand first, what is the core architectural invariant of each type of machine clear? Second, how the invariant can be violated and therefore causing a machine clear. Third, what are the security implications of this invariant violation? And finally, how this violation can be exploited. The first type of machine clear we're presenting is based on self-confined code. Self-confined code is a program storing instructions as data, modifying its own code as it's being executed. Consider this snippet of code where we have a stored instruction modifying the following instruction, transforming it from a load to a no operation. Modern front ends try to maximize the execution throughput by speculatively fetching, decoding, and executing well ahead of retirement. So whenever a self-confined code store instruction targets an instruction already residing in the instruction cache, the processor is forced to flush its pipeline from the speculatively executed instruction, in this case the load secret, and restart from fetching, decoding, and executing the new code, in this case the no operation. But since the SMC detection is not immediate, this creates a transit window where the code and data views of the memory are inconsistent, causing the transit execution of saved code. So the architecture invariant here is that store instructions are always targeting data memory addresses. This invariant is violated in the case of a self-confined code, which targets code memory instead. This violation creates a transit execution window where still code is executed. To understand how this can be exploited, we have to understand the attack primitive which a self-confined code machine clear creates. Speculative Code Store Bypass is an attack primitive which allows an attacker to execute stale and controlled code in a transit execution window originated by a self-confined code machine clear. The primary targets of such a primitive are JIT engines, where usually attacker-controlled code is executed. For instance, take JavaScript code being executed in modern web browsers. SCSB can be broken down in three main steps. The first, keep in mind that on x86 processors, code and data are two views of the same exact memory and are always kept coherent between each other. In step one of our primitive, the JIT engine stores the code of a function f at the address where the code of a function g is. This SMC store instruction will cause a temporary desynchronization between code and data views, where the code view will contain function g, and at the same exact address, the data view will contain function f. At this point, if we call the newly stored function f, the CPU will transiently execute the same code in the code view, which is function g. Eventually, the CPU will detect that there is a self-modifying code and will issue a machine clear. As a last step, the CPU will restore the coherence between code and data view, resuming the execution from the newly stored function, which is function f. SCSB not only affects JIT engines, but also operating system hypervisors, or generally any software storing code and allowing its execution without first issuing a serializing instruction to make sure that code and data views are coherent. So for exploitation, a self-modifying code machine clear yields an attack primitive which allows still code execution, which is somehow similar to its architectural counterpart, a use of the free attack primitive, which operates on no longer referenced data instead. Now I'll hand it over to Enrico, who will tell you more about the second type of machine clear that we're presenting today.
Thank you, Hany. Now I will present another type of machine clear based on subnormal floating-point numbers. Subnormal is a special binary representation for floating-point numbers with a value smaller than the smallest normal number. To better clarify how subnormal can cause a machine clear, let's consider this simple program, where a floating-point division result is used by subsequent operations. Firstly, the floating-point unit will blindly perform the division, supposing that both the operands and the results are normal. In parallel, the floating-point unit will check if the speculation was correct or not. Let's suppose that the result z of the division is a small value in the subnormal range. Since the floating-point unit Arbor is not capable to handle such numbers, the blindly performed operation led to a wrong result that was already forwarded to the subsequent instructions. Later in time, the processor will detect that the forwarded z is wrong, causing a pipeline flash. Finally, the correct result is computed using a microcode assist, and the instructions are re-executed with the correct value. So here we saw that the architectural invariant is that the floating-point unit always operates on normal numbers, and that we can simply violate this invariant by performing subnormal floating-point operation. And that the security implication is that an attacker can transiently inject arbitrary floating-point values. But how can this be exploited? One vulnerable use case that we have found is based on dynamically typed language that uses non-boxing. Non-boxing is a technique used to store a variable type in the unused space of non-numbers. For example, in the Firefox JavaScript engine, this double is used to represent a string value. The upper bits are used to store the type tag, while the remaining lower bits are used for the payload. So, in this example, FFFB is the tag value for the string type, while the payload deadbeef000 is a pointer to the string. Thanks to our reverse engineering efforts, we found a way to craft operands that lead to arbitrary transient null results. For example, by performing a division on the shown x and y operands, we transiently inject the null value shown in the example before. The transient result can be used to perform type confusion in the JavaScript engine that will consider the result of the floating-point division as a string value. Later, after the machine clear detection, the correct architectural result is computed and the JavaScript engine will execute the other branch, the blue one in the figure. By controlling the string pointer bits, an attacker can transiently read arbitrary memory location and use a covert channel to later recover the leaked value. We named this attack floating-point value injection since it partially resembles the load value injection primitive, where instead of load value, floating-point numbers are injected. Additionally, in our paper, we perform a comparison of all the known transient execution windows. In this plot, on the x-axis, all the transient execution mechanisms are reported, while on the y-axis, two attributes are displayed. Firstly, the transient window size that is measured as the number of transient load that can fit in a single window. And secondly, the leakage rate in megabit per second. Please notice that the blue colors are used for Intel processor, while the red ones are for AMD, and that the flash and reload bars are used to show the leakage rate upper limit. On the left, we can observe the transient execution mechanism used by all previous attacks. In particular, TSX is available only on Intel and is no more supported on recent CPUs. All the presented machine clear of this paper are available both for Intel and AMD and present distinguished results. On AMD, self-modifying code can reach more than 160 loads in a single transient window, thanks to the late machine clear detection. Instead, on Intel, floating point obtains the best leakage rate thanks to the quick machine clear detection, combined to the fact that no mistraining is needed. Now, back to Hany.
Finally, we propose a new classification of all known root causes of bad speculation. Existing classifications are based mainly on attacks and not root causes, and therefore they cannot accommodate the new causes of bad speculation presented in this work. First, we have the main classes, control flow and data misprediction, which highlight whether root cause is operating on code or data. Both classes contain their corresponding predictive subclass. While control flow mispredictions are failed attempts to predict the next instructions to execute, data mispredictions are failed attempts to operate on data which has been not validated yet. Then we have the exception subclass, which includes all the architectural exceptions, which has been extensively used in previous attacks. And we also define a new subclass of data misprediction called likely invariant violations, which represents all the architectural invariants which usually hold but occasionally fail. Like, for instance, the floating point invariance, where the floating point unit always operates on normal numbers, and this invariant is violated by performing a floating point operation which operates on the normal numbers. Finally, a subclass representing interrupts, and specifically hardware interrupts, which we observed also generating a machine clear. We can read more about this in the paper. To conclude, bad speculation is not caused only by classic misprediction, but also by architectural invariance violations. Architectural invariance can be exploited, creating new security threats, like, for instance, FPVI and SCSB. And defenses must focus on the wider meaning and the wider class of root causes of bad speculation. You can find the version Gene code, the exploit demo, and more on our webpage. Thanks for your attention.